21, let's go. System of the equations, okay. Infinite solutions, number of A is whatever. You know the thing, it's just, yeah, so there is no Y, okay. This is weird. So what do you have? Just 1, 0, and A. Wait, okay, no, 1, A, and 0, fine. Then this one is, again, the Z component, okay. Y, that is just 1, then this is 2, this determinant is equal to 0, of course, because yeah, if it has infinite solutions, then this should be happening. Oh, and at the same time, actually, what is it's saying is just saying that, yeah, okay, I get it. X, Y, Z, this matrix applied on this thing is equal to that's equal to our zero vector, of course. Yeah, so it has infinite solutions, right? Which means that it has more than one solutions, which means this determinant is zero. That's one thing. But also consider this, that for some certain x, what's happening is that, right, this and that's like, okay, this vector, this column vector is definitely in the plane of these two vectors, right? But moreover, what's happening is, okay, so you can actually write this vector as a linear composition of these two vectors, no problem with that. Moreover, what's happening is that you can write the zero vector as yeah, in that case you can write the zero vector as a linear composition, okay, a linear combination of these two vectors as well, because this can be written as a linear combination, right? Exactly, because yeah, what you have, just have x times this vector, which is now a linear combination. Let's say call this like a vector, b vector, c vector. Then what you have, just have x a vector plus y b vector plus z c vector is equal to our zero vector. But then we know that a vector can be written as some linear combination of b vector plus c vector. So combine, yeah, just get, y plus px, and then that also b vector plus z plus qx times c vector, that's equal to zero vector, which clearly means this thing, that's also just coplanar. So that determinant is also zero, right? So I'm just going to use one of these guys. Well, okay, that is zero, sure. That's obviously zero because this one is a zero vector. Yeah, well, that was unexpectedly simple. So the only thing we have to be looking for is that this, yeah, this thing should be zero, right? Determinant of that should be zero. Okay, that was easy. No big deal, right? Okay, first thing first, you see that just, right, look at that. It's just, so you know that x, y, z, this is actually a nice thing if you don't know about it. If you got x, y, z, then you have something like this: x, then y, and then z, and then you have x, and then y, and then z, right? So always going like this, right? In our columns, if you have this determinant, you can actually write this thing as x cube plus y cube plus z cube minus 3xyz, right? And now look at this thing. You have 1 1 1, that's our x value, this 0 is our y value, and a is our z value. So this is yeah, this can be written as like what, x cube, this is just 1 cube plus y cube is 0, and of course this can be written like this thing is just x plus y plus z, that times of summation of x square minus summation of xy. The good thing is that this thing, for any kind of real value of a, this thing is always positive or equal to 0. But okay, it's not, yeah, it can be equal to 0 when all of these are the same value, x, y, and z. But that won't happen because y and z are clearly different. So the only thing is that, yeah, this thing must be 0. That's the only way it happens. So yeah, a plus 1 plus 0 equal to 0 equal to negative 1 for at least real solutions of a. Might be complex solutions, but who cares? Just a is the answer. Next question. 21 done. Next is 22. Okay, if the system of this equation is inconsistent, then the value of k is, this system is inconsistent. Okay, got it. Right. Yeah, so what you have, just have matrix form 1, 2, negative 3. It's just completely in k, okay. Spread in z, right? Okay, 0. Then the augmented matrix is like what, 1, 3, 0, whatever. Okay. Right, just 1, 2, negative 3, then just 3 plus like 0 0 out there, of course. And then this one is just x, just 2k plus 1, and then there's also z component 0. Yeah, so this determinant must be 0, because if it was not, that would mean that the matrix would have an inverse, which means, of course, there is a solution, but we should have no solutions So the only way this happens is that this matrix should have no inverse, and that would require determinant to be zero, because every matrix can have an adjoint. Only the inverse thing is what, yeah. So the way it has an inverse is that you divide the adjoint by the determinant of a of our matrix, of course. Which means if your determinant is zero, this would be not defined. So clearly your this matrix must have determinant zero, otherwise it will have an inverse, and then you have a solution. Okay, that's awesome. And then also, right, so if that's happening, um, yeah, and this does not have a solution, what does it actually mean? Uh, that means that it's span. So if you apply this on any random vector in a 3D space, yeah, well, that does not ever return this vector, which means, okay, this might be slightly complicated actually. You can think of it like this thing. If this is a, this guy's determinant is zero, right? That means these three column vectors are coplanar. So they're plane, of course. Yeah, you can only have points that lie on their plane, right? Only those points you can reach by applying this matrix on some certain vector, in our case x, y, z. Which means if this lies not in their plane, then you are done basically, right? Yeah. So all we have to ensure is that this does not lie on the plane, and then you're done. Actually, we might just, yeah, we might just want to figure out what the rank of this thing is. We'll leave that for later actually. Who cares? Just figure out the rank, right? Who cares? So how do you figure out the rank of this thing? Gaussian elimination, that's one thing. Number of, okay, think. We could use that one over there to take out some stuff. Oh, first of all, you can use this thing, so you can use that and then subtract some stuff out. Of course, so you can get rid of this type. So you got, yeah, just by row operations, you can write like this thing: 2, 0, 0, 2k plus 1, and then you got 1, 0, 0, then you got 0k plus 3, and then 1. So unless this thing is 0, you can actually get rid of this thing, and that would mean the rank would just be, yes, like these three are actually not coplanar really. Oh, that was that's interesting. Oh, okay, so if this is not 0, then you can get rid of this guy, and that would mean, oh, this is not having determinant equal to 0. So only way this would work is, well, this must be 0. Yeah, it's not 0. Or you could also have this being equal to 0. That would also mean determinant is not equal to 0. And this is equal to, like, k equal to -3. Well, then you can't take out this in that case. That is not going good. Okay, wait a second. Now, if this is equal to 0, then you can actually, you have a 0, 0, 1 vector. That would mean you can get rid of this guy. Just 0, 0, 0, 1, 0, 0, and okay, so you got two vectors, right? Exactly, and another one is just 0 vector. So still, with just these two vectors, so one along the x hat and one along the z hat, we can still cover the complete xz plane. So all you have to ensure is that this does not lie in the xz plane if k equal to -3, and yes, it does not lie on the xz plane. So that's awesome. So either k equal to -3, which makes sense, or you could have k equal to -1/2, which would mean this is just, yeah, this would be 0. You got just something along the x hat and something along the y hat. So it should not lie on the xy plane. So the, yeah, the values of k could be -3 or -1/2. Now, -1/2 is not there, which means it's just A. Next question. 23. Honestly, this does not deserve that much of explanation, but whatever. Since we are all beginners over here, even me, I mean, I have not done this for a long time, so I'm kind of a beginner right now. This equation, okay, these equations give infinite number of values of the triplet x, y, z if. So infinite solutions for this guy. Once again, the same thing. Yeah, so this determinant, actually just write down the augmented matrix 1, 1, 1, 6. And 1, 2, 3, 10. Then what else do you have? 1, 2, n. Oh, wait, are you serious? N. Okay, then I got n over there. Fine. So first of all, this determinant must be 0, right? Okay, you know what? Actually, we could, yeah, just make it slightly different. So we could make it slightly different. Just say 1 1 1 6. Okay, then you got 0 1 2, and that's gone. It's just, yeah, that's what I'm thinking about. The 0 1 2, then you got 4, then you got 1 2 m and n. Slightly better. Okay, cool. So now what should happen is that this determinant must be 0, right? Yes, this determinant must be 0. Awesome. Which is the same as saying just got this determinant 0 1 1 m minus 1. I mean, yeah, just do this. Okay, subtract this row from there, and then you get this thing, and then it's like just 1 over there. You get the thing, right? This must be equal to 0, which means, okay, this is never 0. Oh shoot, wait, this is not 0 ever? Did I miss something? Must have missed something, right? Yeah. Oh, okay, that's not okay. Sorry for that. This is still 1 2. I mean, I just did this subtracted from this guy, right? Okay, just still 1 2 over there. So this must be equal to 0, which means like m minus 1 should be equal to 2. So m should be equal to 3. So m equal to 3, that's awesome. You got that. So just do this thing now. And now we have to see that, okay, this 1 2 3, yeah, this might make sense. Just this determinant must be 0. So you got 1 0 1 1 2 2 and 6 4, and this determinant has to be 0. Okay, once again, you do the same thing. Just get, what do you get? You just get 2 4 1 and minus 1 equal to 0. So more like 1 2 over there, which means like m minus 1 equal to 2. So n equal to 3 as well. So m equal to 3 and n equal to 3. Awesome. Yeah, clearly n equal to 3, right? Infinite number of solutions. That's like 6 4 over there. Maybe, just not maybe. Okay, can I mess up anywhere? It's n over there, of course. Shouldn't n be equal to 10 though? Yeah, I must have messed up somewhere. Well, that's like 2 4, it is still 1 2 over there. So n minus 1 is equal to 2 and equal to 3. But n equal to 3 would mean like, oh god. No, it should be 10. N should be 10. Where did I mess up? Subtract. Oh god, it should be n minus 6 over there. What am I doing? What am I doing? Seriously. It's not 1 1 1 anymore. It's what? You have this thing. 2 4 1 n minus 6 should be equal to 0. Which is like, okay, this is just 1 2 over there. So yeah, n is equal to 8 actually. 8, that's still not helping. Something's wrong. That's 6 right there. It's 4 right there. And why is there a z? Why is there a 1 2 2? That's supposed to be 1 1 2, right? What am I doing today? Just don't get it. So what do you have? Just have 1, then 4, and then n minus 6, right? Okay, that makes sense. N equal to 10, of course. And it has to be 10, such that when you add these two up, you get the equation, right? Exactly. So n equal to 10 and m equal to 3. What do you want? C is the answer. Next question. 24. 24 is the value of lambda for which the system of equation has no solution. Okay, write down the matrix. It's got 2, -1, -1, then 12, then 1, -2, 1, -4, then 1 1 lambda. Okay, and 4. Once again the same thing. Yeah, this has no solution, so of course this experiment must be 0, right? First thing first. Wait, that just gives us lambda anyway, right? Oh yeah. Okay, so this determinant that's not equal to 0, I'm gonna assume that either there's no solution or there is a solution, right? Okay, right, it's a single correct, right? So just figure out when is this determinant equal to 0 and you'll get the thing, of course, right? So just figure that out. Start subtracting. Subtract that out, you just get, okay, weird. Subtract that out first, right? Yeah, we'll just subtract that out. So you get this thing 3 3 0 1, -2, -1, -1, 1, lambda equal to 0, right? Exactly. So then you can write this as just 1, 1 because make that 3 out. Yeah. Using that, you can change this, right? You can just do plus 1, this, okay, plus 2 types of that, it's just 1, 0 in that case. And then this as well, just, or might not change, who cares? So then what you get? I could have just changed this, right? You could just add that to this guy, something, or subtract. Subtract, probably. Whatever, this is actually going to be good enough. So what do you have? Just have lambda times this term, just 1 minus 1. You just need 1, okay, cool. And then you got minus 1 times this minor, which is 2, I think. Yeah, just 1 minus, okay, that's 2, 0. So lambda equal to 2. So D is the answer. Next question. 25. 25 is if delta equal to this thing. Okay, what is this actually equal to? Got it. 0, 100 minus iota. This is iota or what? Or it's just some variable which you don't care about? No, this is probably iota. This probably is in fact iota. Okay. Unexpected. Wait, we don't actually care. We don't actually care because it's an anti-symmetric matrix anyway. Look, yeah, add these two up, it's just 0, add these two up, it's just 0. Of course, so it's 0 anyway. Oh, we don't actually care. So D is correct. 26. This thing is equal to what? So 1a squared. Okay, so this is the type that I have actually written down in one of my videos. So this is what I call the polynomial determinant thing. Actually, did I post that video or not? I don't remember it. If I didn't, I'll post that just after I finish this. So, but what it basically says is that what Pranav's theorem says. Okay, that's just too arrogant. Fine. So what it basically is that 1, 1, 1. You got okay, a b c, I think. Then you got a power n, b power n, and all is the n plus 2 actually. B power n plus 2. Was that the thing? I don't remember it exactly, but whatever. If it require, I'll just change it. So this was equal to it was equal to a minus b times b minus c times, because clearly when you put a equal to b, this is equal to 0, right? B minus c times c minus a, and that times of the summation of a power x, b power y, c power z, and this summation is such that x plus y plus z is equal to, so what's the degree now? I mean, this was n plus 2, this is, okay, it should be n plus 3 actually. It's n plus 3. In this particular case, you have the square, so that's different. Huh. You can't just put -1, that would be so stupid, right? Exactly. You're gonna mess up somewhere. Hey, what's the degree of this polynomial? It's just, no, the degree is not that. It is definitely not that, right? You could just subtract with like b minus c. Yeah, you get all that. And it's like 1 over there, of course. Let's get this guy. So that's out. Then you just have whatever degree you had, that one of them is just out, right? Exactly. So just, oh, then it should just be n plus 1 or something. Let's just say it's n for now, right? For now, let's say it's n. So the way we did that was like we just subtracted one row from other, so you just got b minus a and then b power n minus a power n. So yeah, inside of it just have all the terms homogeneous with degree n minus 1. Similarly over there is n minus 1, right? And that other term, okay, that actually has degree n minus 1. Cool. So just basically this thing, summation of this where x plus y plus z is equal to n minus 1. This was the thing, right? Yeah. Oh god, I don't remember this guy. Or was it? Why is this getting so bad? That's 1 over there, sure. Oh, okay, only 2 of these are out, right? Okay, so then the degree would just be n minus 1, but then you take another one out, so now it's just n minus 2. Right, that was the thing. So actually what should be happening is this should be n plus 2, n plus 2, n plus 2. In this case, n equal to 0. Okay, and then it's just basically this thing. Alright, and the good thing is x plus y plus z equal to 0, that only happens in one way. X equal to 0, y equal to 0, z equal to 0. So yeah, it's just a minus b, b minus c, c minus a. This is the thing. Let's just yeah, see next question. Don't even have to worry. And now you know a more general formula for this thing. So if you had like a cube, b cube, c cube, you just do this thing, but then you have this extra stuff. So summation of a power x, b power x, c power x, such that x plus 5 plus z is equal to 1. Actually, I'm going to show you whether or not this is correct. That will leave that to you. Okay, whatever. Oh, you actually do have this thing. Right. Okay, so as I just said, just have x plus 5 plus z equal to 1 in this case because n equal to 3. Oh, sorry, n plus 2, right? So n equal to 1. So n equal to 1, so that we have 3 over there. So then x equal to 1, y equal to 0, z equal to 0. That's solution. Similarly, y1, x and z 0, and z1, x and y 0. So basically just a plus b plus c. That makes sense? I guess so. So yes, this is actually correct. So if this happens, then the determinant of this, okay, x minus a squared, x minus b squared, x minus c squared. Okay, now these are like multiplied together or something. Vanishes when. This is already true, by the way, okay? I mean, yeah, it's not an equation, it's just an identity, right? Yeah, this determinant vanishes when you got 1 over there. You got x minus a squared, x minus b squared, x minus c squared. These are different squares of these guys. But then now these are like multiplied together. That's different than anything I've ever seen. You could just take x minus a, x minus b, x minus c common, and then some stuff would happen. But no, that's just not doable. Or you could just do x squared, x squared, x squared. Okay, yeah, that might help. Honestly, it won't. I guess we'll just have to go from the basics in that case. So we'll just subtract the first column in every other column, right? So for this guy, just x minus c common, then subtract this guy, just get what? B minus a. Okay. Then you got x minus c over there, subtract this out. Okay, got minus c over there as well. Hopefully something nice will happen. Isn't there some better way to do this? Okay, first of all, maybe we should not be doing that. We should be doing this thing. If you got 1 a square, 1 b square, 1 c square, and you have this thing a b b c a c, what's this going to be, right? Unexpected. Very unexpected, actually. You could just subtract. You could definitely just subtract. So, subtract this row from this guy. So, what do you get? Or do something else. No, it's just better to subtract this row from that. So, you will get what? A common just got b minus a, right? So, just, oh, okay, that actually goes out. Awesome. So, you got b minus a. Then, b is common, you got c minus b, c minus b. And then you got c is common. Just have a minus c, or you could add like this thing a minus b, b minus c, a minus c. Okay, it's just basically square of this guy because that's also going to give us the same thing. C minus a. This complete thing is just squared. Yeah, that's what this thing will be. Right, this is actually irrelevant to this completely. Ha! Awesome. So yeah. Because then just 1 a square, okay, all that stuff, right? Exactly. This is a degree 4 if you want, and this is degree 4 as well, but it's different. Like, yeah, both of these are very different actually. Whatever, so this is the thing. I guess you should use capital A, capital B, okay, this is equal to 0 when either A equal to B. So you just have x minus A equal to x minus C or something, which would mean B equal to C. Okay, then same thing, just repeat it. So you got A equal to B or B equal to C or all that stuff, right? Exactly. I guess that would be the thing. Can it actually vanish otherwise? I mess up somewhere. How is this relevant to that? I don't think it should be. Yeah, it definitely should not be. Oh shit. Uh-oh. Yeah, that's a bit of a problem over there because when we took that, yeah, when we took that B minus A out, the whole row was not having B minus A. Right? This is of course just incorrect. You can't do it like that. I guess we'll just go the the usual way. So what we'll do is just subtract this column from that column, just get this thing 1a squared. You know what, actually even skip that, we don't actually need to write that. What do you get? Just get b squared as a squared. Yeah, then you got c squared as a squared. Or if you want, you could have first subtracted this from that, just get c squared as b squared in that case. Awesome. So you get c squared as b squared, then you get c times of a minus b. Over here, what you can just get b times of c minus a. Right, that's cool. So now what? Now you got b minus a over there, and that's not there for some reason. I was expecting something very different from this guy. That is unexpected. Oh, right, that's unexpected because it should actually be BC, and then that's actually different. So BC, AC, and AB. Then what you would actually have is, just A times of B minus C, and then what you just have C times of A minus B. Okay, awesome. Now you can take that A minus B out. Just get A minus B. And also, you know what? Just put negatives over here and a negative over here, because who cares? Huh? Yeah. Okay, actually we want this to be 0 anyway, so who cares whether or not you want to put that over there. Okay, awesome. So this is the thing. So either A equal to B or B equal to C. In this case, when I say small a, actually I mean this complete thing, x minus small a, right? I should have really used capital A, capital B, but whatever. So that would be the thing. And they're saying A, B, C are all different, so this can never happen. So that's out of the window. Okay, cool. So what do you have? Just have this thing, A plus B and C, and then B plus C and A. This guy should have 0 to 0. Okay, of course, that's the thing. Now what? Just replace it by what it actually should be, just 2x minus A minus B. Then you got 2x minus B minus C. Then you got x minus C and x minus A. This has to be equal to 0, right? My two suggestion, I actually add this. So add this to that. So you just get 3x minus A minus B minus C. That could equal to 0. Or you could just have this determinant 1 x minus C, 1 x minus A. Which, okay, that's once again given the same thing, that these should be the same, which will never happen. So what do you get? Just get 3x is equal to A plus B plus C. Yeah, so B is correct. Next question. 28. 28 is if alpha beta gamma are the roots of this equation, when this determinant will be. Okay, so I just did that, right? Oh, it's slightly different. No, it's not. So you can just actually revert these two rows, sorry, these two columns, right? You can exchange these guys. So what do you have? Just negative alpha beta gamma. Then you have this thing, gamma alpha beta, and then beta gamma alpha. So now that's the form that you actually want, right? Alpha beta gamma, alpha beta gamma, alpha beta gamma, right? And you know this thing is just that, so like it's just summation of alpha cube minus 3 alpha beta gamma, right? Exactly. So if x square plus, okay, in alpha beta gamma are actually the roots of this equation, right? There's a cubic term or what? Okay, cool. So there's a cubic term. So you can write alpha cube as just negative of p alpha and negative q. So this thing just becomes what? It just becomes summation of p alpha, okay, plus q, right? Yeah, because it just changed everything in negative, of course. And you got plus 3 alpha beta gamma. Awesome. And now it's just a piece of cake, because guess what? Summation of alpha. What's that? 0. So that term would not actually exist. Then just summation of p just 3q. And what about this guy? So alpha beta gamma is just negative q upon 1. Yeah, just negative q. So it's just minus 3q. Oh, that's awesome. Just 0. So this happens to be 0. Not unexpected, is it? Yeah, definitely not. Because alpha plus beta plus gamma equal to 0, and this actually has a factor of alpha plus beta plus gamma. So D would be correct anyway. Next question. 29. What am I doing? Okay, 29. 29 is if delta equal to this thing, it's a polynomial. Then P5, P6 is. So what do you want? You want this and that, right? Interesting. So the linear term and the constant term. Well, constant term is easy to find. Just put 0 over there. Negative 9 is supposed to be the constant term most likely. We'll try to find the linear term somehow. So how do you actually figure out the linear term? That's what the linear term. Anything in well x plus 1 I think plus 1 seems pretty symmetric for something that should. Oh wait. Oh, it is actually very symmetric. Look, x plus 1, then x plus 1. Okay, alpha, beta, gamma, alpha, beta, gamma, alpha, beta. Okay, that's why they put just before this question, right? Okay, cool. So yeah, it's just basically this thing. It's just some of these guys just oh, we actually don't need that, do we? Yeah, we don't. We really don't. So what do you have? Just have x plus 1 cubed plus x times of x plus 1, this guy cubed plus x squared plus 2 cubed. That minus 3 times of the product, which is x plus 1 squared times x squared plus 2. Now all you want is just linear terms, right? Of course. So yeah, from here you only want linear term. You could just say that x squared and other terms are actually negligible if you really want. So this would by binomial theorem, it's just approximately 1 plus 3x. Okay, then this guy would have x cubed anyway, so ignore that completely. This guy has no linear term, it just has plus 8 instead of a constant term. And what about this guy? Well, there's an x over there, so if you want a linear term or you want a constant term, you have to have constant from these guys. Just 1 square times 2, of course, which is 2. So there you go, just 2 times of x is negative 6x. That makes sense. So yeah, to first degree approximation. I'm not really talking about approximations now, but yeah, it's a nice tool when you want to figure out what this linear term should be. So you get just 9 minus 3x. Awesome. So this would just be 9. P6 is 9, I hope. Or is it? It's negative 9 everywhere I see though. Did I mess up somewhere? Was it still negative? Oh, okay, of course. So the thing is like, no, wait, you didn't actually switch it. No, you didn't. You did not switch it actually. Okay, then how did this happen? Uh, Wait. Now that is the thing, alpha, beta, gamma. Then this is just alpha, beta, gamma. Wait, what? Clearly, that must be the thing, of course. It is just that, right? Just solution of these guys cube minus 3 times of that. Okay, yeah, that is the thing. So then, how does this not help? Right, it should actually be this thing. It should be negative 3 and 9. That's not there. It's negative 3 and negative 9 for some reason. How could it be negative 9? That doesn't actually make any sense, right? Unless you just had negative over there, but that's not the thing. It's just not there. Okay. God. No, it should be negative 3 comma 9. That's not there. Because there's no switching involved. It's just the usual thing. For some reason they are not accepting that. I don't know. It should be just negative 3 comma 9. Next question. 30. Square matrix A equal to this thing in which aij equal to 0 for I not equal to j and aij equal to k. So, okay, diagonal matrix, right? It's just k, 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 k everywhere, right? So basically this matrix is just k times of the identity matrix, whatever. For I equal to j is called a diagonal matrix. That was an easy thing. Or a scalar matrix actually, because this is the same thing everywhere. So if you want even more precise, it should be scalar matrix. So B is correct. Next question. Because it's a scalar multiple of the identity matrix. Okay, 32. I guess so. I mean, actually, it's called scalar matrix because what it does on a vector is that it just scales up by k. That's why scalar. Anyway, 32. Oh, 31. What am I doing? 31. AB are square matrices of order 3. A is a non-singular matrix and AB is not. AB is equal to 0. Okay, okay, okay. Wait, A is a non-singular matrix. That just means B has to be singular. So remember of B is 0. B is a singular matrix. That was easy, isn't it? Yeah. Oh, in fact, you know what? Because A is non-singular, it has an inverse. So you can apply A inverse on both sides. Just get A inverse A, just identity matrix that applied on B, just B itself. So B is equal to A inverse applied on the 0 vector. Okay, no, the 0 matrix. Yeah, but that makes sense. So that is just the null matrix anyway. So what do you get? You just get B is equal to 0 matrix. Essentially, that's what you get, right? So yeah, it's just null matrix. So B is A. I mean, the null matrix. 32. 32 is this matrix is known as upper triangle matrix. Come on, are you serious? This is just fine. Symmetric, no. Diagonal, no. Skew symmetric, no. C. That is thing 33. In an their grammar. Okay, in an upper triangular matrix, so something like this, of course, n times n, minimum number of zeros is minimum number of zeros. Ah, right. So if all of these guys, which are not supposed to be zeros, are actually not zeros, then awesome. That would mean it's the minimum number of zeros because otherwise you would have more zeros than what are the minimum. Okay, so yeah, just n cross n, right? Look at this guy. The first guy just has n minus 1. The second guy has n minus 2. This guy has n minus 3. So sum till n minus 1, of course. Start off at 0 till n minus 1. That makes sense. Right, which just happens to be what? N minus 1 times n upon 2. So that is A. Yeah. Next question. 34. If A is equal to this guy's scalar matrix, then place of A is scalar matrix. Yeah, I get it. Summation. Okay, what? Yes, that's actually the correct thing because for some certain I, when you sum this along J, yeah, you just get this, you just get the diagonal element for that particular I, and then you're just summing up. So yes, actually A is correct because it's scalar matrix, right? B summation along I. Wait, what? But you don't know what J is. So what do you mean by this summation actually? I don't know what that means. Really? Okay, just along J. Oh yeah, so like B is correct and A is correct. I think they want us to do D, but then A is also correct, so why should we not? Right? Yeah, I mean, this is just weird. Yes, it's summation of A, I, but look, like A is also correct, so then D and A, that would mean it's not single correct. And I've been solving multiple correct questions as if there was single correct all this time. Oh shit. So for example, for 31, B is also singular matrix. You should, and then similarly for 30, it's, yeah, okay, I get what's happening. It's a scalar matrix as well as it's a diagonal matrix. So B and D. Oh no. This at least does not have multiple solutions, so that's good. Yeah. Oh, this is not going good. Fine, whatever. So 30, that was more than one correct, it seems. So it's not just a scalar matrix, it's also a diagonal matrix, which is D. 31, transitional matrix, which is a singular matrix as well, so B is correct. Okay, 32. That was at least only a single correct. Okay, 33. Yeah, that's correct. Okay, fine. What is this? Are you serious? 2n times n minus 1 upon 2. How does that actually make any sense? Okay, whatever. If A is equal to, yeah, it's matrix of, then A and D are correct, right? Okay. 35. 35 is if A equal to this thing. Ah, of course, the usual rotation matrix. So, like let's just say you apply e power I alpha on something like x plus I y, complex numbers, of course, right? So what you can just get like x cosine alpha, then minus y sine alpha, right? And plus iota times what? So you just got x sine alpha plus y cosine alpha, right? Exactly. Which, if you think about it, if you think of these complex numbers as vectors, what actually is doing, like, yeah, this thing is rotating this vector by alpha, right? And what you get is this thing, which can also be written like this vector is just x cosine alpha minus y sine alpha, and then x sine alpha plus y cosine alpha. And guess what? You can also write this as this matrix: cosine alpha minus sine alpha, then cosine alpha. And yeah, like, okay, and apply on x and y, of course. So yeah, guess what? This is a rotation matrix. Like this rotates by alpha, and over here, what you're actually doing is where that go? Right, it's negative sign alpha over there. It's as if you replace alpha by negative alpha, so it's rotating in the reverse direction. So this rotates it, and it rotates it clockwise, right? That's what it does, clockwise by alpha, of course. So then a squared just rotates by 2 alpha clockwise. So then it should just be that. Exactly, just C. So that's no big brainer. Next question. And if you really want to do it, right? Do the matrix multiplication. This is the same thing anyway. All right, next question. If A is equal, is there some other option that might be correct? No, it's not. It's just, okay, if A is equal to this matrix and A square is equal to this, okay, then 36, okay. Let's see. So it's A, B, and oh, that's a symmetric matrix, isn't it? Right, its transpose is the same as that, so, yeah, just the square of this vector. Yeah, whatever, just do the thing. Okay, it's A, B, A, B. Wait, no, it's A over there. Then you got A, B, A, B. What do you get? The first vector applied. Okay, this matrix applied on the first vector is just, you got this column vector A squared. Then you have plus B squared. You know, I just got AB plus AB. It's like 2AB basically. And by symmetry, you would say this is also going to be the same thing, right? Yeah. Well, it's no different than that, of course. Yeah, that's what happens. So this is the thing. Then alpha is a squared plus b squared, beta is 2ab, no big deal. B is correct. Do they even have to put such questions? 37. 37 is if a equal to this, okay, then a power 4n equals, yeah, of course. So it's like it's like iota times the identity matrix, so a power 4n, that's just iota power 4n times the identity matrix power 4n, which is just identity matrix itself, so that is just a. Yeah, yeah. Next question, 38. And by a I mean the option A, not capital A. Okay. If a is equal to this, b is equal to that, and a plus b squared is equal to this thing, value of a and b is. Right, so you know, like a squared. Okay, wait a second. A plus b squared is equal to a squared plus b squared now. That's the same thing as saying ab plus ba is equal to 0, right? Yeah. Or like ab equal to negative ba. Interesting. 1, 2, negative 1, negative 1. Think about, like, these are just 2 by 2 matrices, aren't they? Yeah. AB equal to negative BA, huh? This is very weird. Well, we'll see what happens. First of all, just actually, figure out what AB should be. Or is there some better way to actually not go into all that? Got AB1, negative 1. No, I guess we just have to do it, right? So what's AB going to be? AB is this, is just, okay, 1, 2, negative 1, negative 1. And then you got this guy. AB1, negative 1. So the first you got AB, this guy just A minus B, then you got 2A minus B, then this one is just 1, plus 1 is just 2, then you got 2 plus 1 is just 3. Okay, what's BA going to be? BA is just this thing, copy paste of course, so copy this guy, paste over here, right? Yeah, so what do you get? Just get this thing. First this vector, so what do you get? Just get A plus 2, then B minus 2. Yes, then this vector was over there, just becomes negative A, negative 1, negative B, positive 1. Nice. Yeah, I guess that's right. Okay, so what should happen is like this plus that should be equal to the 0 matrix, right? Yeah, that's what I was thinking about. Okay, cool. So A plus 2 plus A minus B is equal to 0. So what do you get? Like 2A is equal to B plus 2. That's first equation. What else do you have? Well, that addition is just okay. It's negative A plus 1 equal to okay. A equal to 1. Awesome. A equal to 1. and then do the similar thing over there. Just need to be okay. That is like b is equal to -2, it seems. Yes. So equal to -2. Does this help? Does this work? 2a equal to 0. No, that does not. That definitely does not work. Oh shit, it's 2a plus 2 over there. Sorry for that. It should be this thing. 2a plus 2 is equal to b, which yes, it works out because wait, it doesn't. No, it doesn't. That's not right. Can't be having that, right? No. It's like 2a plus 2 plus b equal to 0. I guess. Wait a second. This plus that equal to 0. 2a plus 2 minus b equal to 0. So like 2a plus 2 equal to b, of course. Then similarly over here, just get a. So minus a plus 1 equal to 0. Over here, just get minus b plus 4 equal. Oh god, b should be equal to -4. Not even negative, it's like equal to 4 itself. So equal to 4. This helps? Yes, this actually works out. Okay, cool. What about this guy? So just 2a minus 2 equal to 0, a equal to 1. Yeah, right. Yes, then that's the thing, a equal to 1, b equal to 4. Which is b? Next question. 39. 39 is let f be equal to this. Alright. So the thing is it's not transforming the z anywhere. It's like, yeah, if you apply this on x, y, z, then the z component will still be the previous z component, which is z itself. It's just that xy plane stuff that's rotated. That's all it's doing really. Then f alpha dash. What is alpha dash? Oh, it's just some other angle. Who cares? So yeah, just equal to f of alpha plus alpha dash. Yeah, alpha plus alpha dash was like rotating by alpha anti-clockwise and then once again anti-clockwise in the xy plane. Right? It's not changing the z component at all. So just remove that. This is the same thing as saying this matrix. Cosine alpha, sine alpha, negative sine alpha, cosine alpha. It's no different than that because if you get rid of the z component, if you don't think about it, just dealing with the xy components, then it's just rotation matrix itself. It's not doing anything else. So yeah, this is C. Next question. Oh, it's 40, right? We don't want actually 40. We want 39, right? So 39 is the order of x, y, z. Okay. Oh, that's actually a row vector, isn't it? Right. So this box, it's not actually the determinant. It's not that. All right. It's just not that. Oh yeah. Okay. This I've seen. Recently, actually, I've been learning about conic sections and how you can use determinants. So, sorry, how you can use matrices and stuff to simplify them to a certain extent, right? Or like organize them better, you could say so. So then this thing, right? What is this thing is like dot whatever vector you'll get after applying this matrix on our xyz with xyz, right? So that is a number which is just 1 times 1 matrix. So yeah, just b. You even have to worry about this. 39 is b. All right then. So 20 more questions done. And then how much is remaining now? 55. Okay. So in the next video, I'll do 15 questions. Wait, no. Oh, yeah, okay, I will do 15 questions first. Right. So that's it. Let's see you guys in the next video. Bye.